So let's see if we can understand where these lines are coming from. All right, so what's happening is that this discharge, not only does it pull the H2 apart, break bonds, make hydrogen atoms, but it puts some of those hydrogen atoms into these excited states. And so a hydrogen atom might be in this excited state, this initial excited state, high energy state. And of course, that's a high energy state. It's unstable. The system wants to relax. It wants to relax to a lower energy state. All right? And when it does so, because it's going to lower energy state, it has to emit radiation. And that radiation is going to come out as a photon whose energy is exactly the energy difference between these two states. That's the quantum nature here of the hydrogen atom. The photon that comes out has to have an energy delta E, which is exactly the energy of the initial state minus that of the final state. And therefore, the frequency of that radiation is going to have one value given by this energy difference divided by Planck's constant H. So that's what's happening in the discharge. So what we've got is we've got some hydrogen atoms excited to, say, for example, this B state, which is a lower energy state. And so when it relaxes, there's a small energy difference between here and this bottom state. Therefore, you're going to have a low frequency of radiation. If you have some other hydrogen atoms in the discharge that are excited to this state up here, well, this is a big energy difference, and so delta E is going to be large, and therefore you're going to have some radiation emitted that's at a high frequency because delta E is large. If it's at a high frequency, it's going to have a short wavelength. These hydrogen atoms are going to have a low frequency emission. It's going to be a long wavelength. All right, so we've got a mixture of atoms in this state or in this state or in any other states in this discharge.